Today we're going to look at the energy in reactions. This is going to go back to those energy diagrams where we did the LOL charts. And really what we're focusing on is the energy of the chemicals involved in the reactions. There are two types of reactions that involve this change in energy. We've already talked about these before, but now we're talking about them in terms of the chemical energy and not just the phase and the thermal energy as before. So an exothermic energy is released or exiting the system. For an endothermic, it is going in, it's being absorbed or going into the system. Here's an example, sodium hydroxide, NaOH, dissolving in water. This is going to release energy, so it's exothermic. When you go to write out the equation for this, you have NaOH is Na plus and OH minus, and then plus energy. So energy, if we drew our LOL graph, energy would be going out of the system. This would feel hot. Because energy is a product, it's going out of the reaction and into your hands. You would feel hot in this case. Here's how we can look at this. So there's a lot of energy in the reactants and a low amount of energy in the products. So as we're converting our reactants into products, we are going to release energy out into the system. So this energy goes somewhere and it goes out of the system. Another example would be ammonium chloride, or NH4Cl. And this one absorbs energy. So it needs energy to get this reaction going. During this reaction, we find that the temperature goes down, so it feels cold. And we know that when something feels cold, it's really pulling the heat, the energy out of our hands. So this is endothermic for an LOL graph. Of this reaction, we would have the energy going into the system. And since it has to go into the system, it acts like another reactant, so it's over here on the reactant side. So energy plus NH4Cl enables it to split apart into its NH4 and Cl. So without this added energy, this reaction can't happen. It has to have energy to go. So NH4Cl is fairly stable until you give it some energy to split apart. Okay, so here is a diagram showing the energy level. So again, we have reactants down here, products up here. To get from the reactants up to the products, we have to add energy. Just like if you wanted to have a marble race down a track, or say a Hot Wheels car race down a track, you have to give it energy by placing it at the top of the track. Well, here we have reactants. We have to give them energy to get up to the products. So this can't go unless we add energy to the system. Okay, so back to our LOL graphs and that reading we did so long ago where we talked about E for phase, or EPH, which is phase energy. This represents the amount of energy that the matter is holding based off of its phase. So either for the solid, where we have, it in a nice little pattern, and these particles aren't moving very much, so, there's not a lot of energy here, whereas with the liquid, we have, a little bit more energy, and then the gas, is all over the place. And we have the 1 bar, 2 bar, 4 bars. That's not changing at all. Next up, we have the thermal energy, and that's when, we're talking about the motion of the particles. We say around 0 is 1 bar, room temperature 2 bars, evaporating 4 bars, or room temperature is, that 20 to like 30 degrees Celsius. Evaporating is like 100 degrees Celsius. This 0 would be like anytime it's mentioning freezing. And then this last portion, which we've kind of been ignoring until now, is the ECH, this chemical energy. And this is the energy that's holding the atoms together. So you have this atom that is bonded to this atom. This bond right here is what we're talking about that's holding the energy. There is energy that is keeping these together. So either we have to put energy into the system to make this bond, or we have to take energy out of the system to break this bond. You can also put energy into the system to break it, but we have to mess with energy, either putting it in or out, to break or build this bond. And it just depends on what the type of bond is. Okay, so ETH and ECH. For a reaction to happen, particles have to hit each other. They have to touch to be able to form a bond, or they have to break away from each other. So there has to be some sort of collision to get a reaction to go. So particles need to hit. This is called activation energy. It's this amount of energy it takes for the reaction to happen. They have to hit with enough force to cause them to react. When we have a very slow, cold-moving particle, there's not a lot of energy there. And we already know this. We've already talked about this before, that these low-energy particles tend to be slower. They measure colder when we use thermometers. There's not a lot of energy there. High-energy particles tend to be faster, and they hit harder. They contain this activation energy on their own, whereas the low energy particles tend to need some help to get that activation energy, to get that reaction to happen, which is why we put our food in the fridge. Breaking down food is a chemical reaction. If we can slow that down by cooling it, then we can keep our food from going bad. So that's why your milk gets put in the fridge. And if you leave the milk sitting out, just adding a little bit of energy from the room temperature will cause the reaction to take place and your milk will spoil. So, slowing things down, making them colder, that can change the energy available and possibly reduce it so that we don't have enough energy to make a reaction happen. Okay, looking at activation energy and speed of particles, that connects the chemical energy and the thermal energy. You can't change one without changing the other. So this is how those LOL charts are going to come into play. We're going to be able to monitor and follow these in our LOL charts. Okay, here's an example. We are burning CH4, methane. So we have our methane gas and our oxygen is present. We produce CO2 and water and then energy. And this would be the fire. We get light as well as heat. So this reaction produces quite a bit of energy. We have there's a lot of energy stored in the CH4, so that means we have a pretty high ECH. And then our products, the CO2 and the H2O, don't really have a lot of energy. So this is dropped down, and what we see is we have 4 to begin with. We lose 2, so we're left with 2 to end. But this isn't the whole story, because we have this fire, we have this heat, and heat changes temperature. So we have to look at the thermal energy as well. So what we see happening is that there is a middle step. So ECH is going to transfer its energy to ETH. So those 2 bars that we saw in the last slide that left the system are moving over to ETH. And so we have these 2 bars are now hanging out here. Our chemical energy is back down to where it should be. It's back, or it's dropped to the product level, which is much lower. But we have this increase in temperature. Notice nothing has gone in and out of the system because we have 6 bars total here and 6 bars total here. So there's a plus 0 here. Okay, we haven't added or taken any out of the system yet. We have just transferred energy from ECH over to ETH. Then, now that we have these 2 bars here in ETH, they are going to leave the system through heat. All right, if your hand was on in the fire while this was going on, if you were holding on to the methane, you would get very, very hot and very burned because that energy would be released by heat. And we use this to heat our homes or to cook our food. When we use propane heat or any of that, we harvest this energy that's leaving as a heat source for us. So what we're left with is a room temperature product, and that has a low level of energy. So the whole thing is set out like this. So it's now called an LOLOL, so laughing out loud graphs. And what we did before was we took these 2 bars, moved them over to TH, so they're right here. And then those 2 bars left the system here. So we're back down to our original temperature and low product energy. Okay, let's look at it the other way. So sometimes we have to add energy to get a reaction to go. And here's calcium carbonate. And to break it up and make calcium oxide and CO2, we need to add energy. So energy is a product. Now, there's no way to add chemical energy into a system. So what we're doing is we're taking these 2 bars of energy and we're placing them here. We're increasing our chemical energy of the system. So if we drew our energy of the graph, we would have something that looks like this with our reactants here and our products up here, which is what we have here. We have this low part and then this high part over here. But since we don't have an energy source here of chemical energy, we only have it as heat. So again, we have to use the ETH. So what we do first is we have this room temperature sample. And we add heat to it. So these bars are these 2 right here. So we've added heat to the sample. We're cooking it. We did this in the magnesium oxide lab when we put the magnesium inside the little ceramic dish and we set it over the fire and we saw it glow. By putting that fire underneath, we were adding this energy here to it. So we heated up our reactants. Okay, then this heat gave its energy over to the chemical, and we were left with products that were high energy. So these are high energy products, but they're at room temperature. Okay, so that energy, that fire and everything that we've added into the system has been converted to chemical energy. So looking at this whole thing, we start out with cold reactants and we add in some energy by maybe placing it on a hot plate or putting it over fire. And that increases the temperature of the reactants. We get them moving a little faster, hitting a little harder. So during that process, the energy is transferred over to ECH, and we have some cool high energy products. Okay, so this reaction, is this reaction an endothermic or an exothermic reaction? Okay, we see this as being endothermic. One here is having it go in endothermic. But if we walk through this, we take this energy and we are going to put it over in the chemical. So 1 bar here gets moved over to right here. But that makes the products very, very cold. So we put energy into the system to warm it back up. So here is this energy that is going into the system, and we warm it back to room temperature. Generally speaking, you're going to want to end with room temperature